And I hope to kind of give you some examples of this. And just, I'm not going to spend a lot of time on a very general introduction, but in the simplest way, optimization is just using the minimum amount of material that you need to achieve your task, right? Nature is very, very good at this. You guys have all heard this before, but it's true. Material is very expensive in nature. You need to, as an organism, use the minimum amount of material if you're going to survive, right? This is absolutely not the way human construction works. Our materials are artificially cheap because carbon is not costed, and we tend to throw a lot more materials at the problem than shape, okay? The only mathematical slide has no actual equations, but from an engineering perspective, all optimization is taking derivatives and setting them to zero, okay? So you have some cost function you're trying to minimize. Can be monetary costs, can be carbon, two very different things, unfortunately. You have some design variables you're allowed to change, right, to minimize that cost, to get you to the bottom of the bowl of your cost function, right, where your derivatives are zero. And you have some constraints, which are basically for us in the engineering side, structural safety, but they can include architectural usage constraints, right? If you have those three things, you have a well-defined mathematical optimization problem. It's a little bit different than just pure engineering design, right? There's another layer of math on top of it, okay? There's sort of three conceptual types in increasing generality, or most engineers spend their time being asked, what's the size? They're given a shape, they produce a size. If you step another level up from that and you're allowed to change the shape, you can really improve your efficiency, okay? You step another level up from that and you get to ask what's connected to what, okay, that's topology. Then you're really in the broadest possible space where you have the most possible benefit. So this is something that, you know, I think we as engineers often struggle with. I'll get into that in a little bit. But sizing optimization is essentially a solved problem, okay? There's a really excellent paper from 1992 by one of my former colleagues, Bill Baker at SOM. It's a whopping 4 pages that just adapts a literature of optimization that's existed for a long time to practical structural engineering practice. Everybody at any other large structural engineering firm basically copy-pasted this paper and works with it in the very sexy, sophisticated, interactive medium of a Microsoft Excel spreadsheet. So this is kind of a solved problem. We need to use it more than we maybe do, but it's definitely out there. If you step that level of generality up and you're allowed to change the shape, you're in the world that you guys recognize as form finding, right? Which has a long storied architectural history. Briato's soap film structures, Anthony Gaudi's hanging chains, maybe you recognize Heinz Insler's hanging fabric models. All these techniques can be replicated computationally, refined computationally. That sort of capability has existed again, at least since the 90s, right? And it just keeps improving. Topology optimization is a little bit more recent. It's a wider realm. It's usually kind of computationally implemented by taking a sort of design domain and iteratively removing underused material. It's a little bit messier in a lot of ways, but it also can give you kind of broader ranges of insight. It has been implemented on a couple of buildings, right? But it's something that, you know, we're still kind of exploring on the technical side. And you're kind of sensing a thread here, which is that this isn't necessarily new technology, okay? And my one polemical slide is that I would not say that the barriers to getting truly optimal designs are technological. I think they are disciplinary and frankly political, right? So architects can be dogmatic. You got to give us room to be able to change the shape if you want to give a better result. Sorry, but it's true. Engineers can be uncreative and reactive. They're taught in school that the architect produces the geometry and they design it. It's a terrible disservice we do to engineering students to tell them this. They need to be able to think a lot more proactively about what designs are actually going to improve the structure, right? And my former mentor, Bill Baker at SOM, would say, like, architects need to view, or engineers need to view geometry from the architects as a statement of a design problem. and then respond to that design problem. I think that's a really good word of advice for us on the engineering side. Those of us who kind of think that way are often in the kind of AEC tech camp here, the Chicago Innovate camp of, being computer jocks who are a little bit attached to our technological solutions. And we need to be able to work with architects to give them ownership of the designs, not just sort of advocate our favorite algorithms. This is kind of an engineering problem. All of that is kind of dwarfed by the contracting problem. Carbon is not cost. Cost tends to rule everything. I really hate being told at conferences, I've heard it a lot at this point in my career, that you, the entrepreneurial practitioner, are going to go out and convince clients to save carbon. That will work in maybe 5% of cases, if you're lucky, with the right clients. There needs to be a mandate that prices carbon at real cost. And in a lot of ways, these sort of inspirational stories of applying optimization technologies are just positioning us to be experts when that happens. They're not really moving the needle like it needs to happen. The mandate has always been the solution. I'll give a couple of examples. This is from my work at SOM, of kind of form planning and optimization. This is really about architectural engineering collaboration. I think it's a good example of how that can happen well, okay? So 2 towers in Hangzhou, China. The part that I'm going to focus on is this catenary drape hanging between the 2 buildings. That is really a free-spanning structure. You're very lucky, right, that the architectural brief for this said catenary, okay? They had the right solution for the shape, but that doesn't mean it was fully worked out. What we needed to do on the engineering side was take that correct solution, a catenary, hanging steel sections, and sort of scale it, translate it, trim it, right? So we got flat panels across this doubly curved surface. Those are all exactly flat panels, and a good looking architectural solution. That's something that engineers really need to take seriously, and that I try and advocate. But that is all within the sandbox of catenaries everywhere for gravity, flat panels everywhere for construction. There's a lot of detail into how this was actually set up in terms of the orientation of the members. I don't really have a lot of time to go into, but we did kind of orient the steel eye sections that are making up this grid so that they had a logical, clean node that did not need to be aggressively CNC milled. I think they didn't need to use CNC milling. So I can't say that we avoided that. But the concept was like, in principle, you could do this with just ordinary shop tools, even if you didn't end up doing that. And grasshoppers really changed the way we work. Like I said, I kind of graduated as a computer jock. I thought I could kind of give architects an algorithm that would solve the problem for them. That doesn't work in practice. What does work, what I found to work in this type of project, is defining a grasshopper logic, writing your own grasshopper scripts that give architects parameters to be able to design with, right? And really responding to them when they hit the limits of that script. So, I had to be at the architect's desk like sometimes 3 hours a day, saying, okay, this is where it's breaking. Okay, how can I change my algorithm so we're still in a good structural sandbox, right? But it gets the architectural, hits the architectural design goals. And this it's kind of a way to force that conversation, like in its particulars, right? It's not like one algorithm fits all. You're going to be doing this custom on a bespoke basis for each project. And frankly, it's kind of annoying to do this, like for both architects and engineers. It's like out of our comfort zone to be sitting at an architect's desk 3 hours a day, right? And it's kind of annoying to them too, but I don't seem to mind that. So I think the result is pretty inspiring. It's kind of the structure is the architecture in a lot of ways, I think we wove those two together pretty well. And the member sizes are quite small, so it creates a kind of nice space. Another example here, I'm going to shift gears from that architectural engineering collaboration and talk more about getting things through the contractor side, okay? So this is a project, a much more recent one that I worked on at Thornton Tomasetti, where we're looking at a grid shell that's covering part of the Columbus Airport expansion, okay? In this case, the architects kind of they gave me basically carte blanche to kind of come up with ideas for this. In that case, the collaboration was fantastic, right? It was kind of just thumbs up, thumbs down, does this look good or not? But then getting it through the project that had budgetary challenges was a whole other thing. Okay, and getting a good result out of that. So the original sort of sketch was sort of triangulated surface. For these type of grid shell structures, one thing that I'll say is don't use triangles. It's lowbrow. You don't need triangles to make things flat face. You can definitely use quads. It's going to make your detailing easier. From a structural perspective, a really important part of this is that it had to drop in on the rest of the structure without forcing thrusts into it. Okay, it had to be self-tied, is what we said. You got to think of this as almost like its own modular solution that supports everything but its own vertical loads, right? It's not arching to the rest of the structure. That just complicates things. So from an organizational perspective, it needed to be separate. So starting from that triangle mesh, you can come up with a quadrilateral mesh with all flat panels. This has gotten way easier, guys. You can do this in Kangaroo now, right? You used to need specialty software to be able to do it. Rounded corners was kind of an architectural design decision. Reducing the panel sizes was a constructability constraint. You had to be able to have sizes that were easy to fabricate and ship that didn't incur extra costs, right? And I should back up and mention that there is a form finding, like structural form finding process going on in the background here that was innovated by my former colleague and current academic research collaborator, Cameron Millar. So all that stuff, self-tied flat panels, is kind of contained in some academic research papers that he wrote. Like I said, don't use triangles if you can avoid it. You're going to waste more glass. You're going to make your node detailing more complicated. You don't need to do this anymore. There are accessible techniques to force flat panels on a doubly curved surface. So we did a lot of work on the TT side, and before the contractor was brought on, we had these flat panels. We had all panels below this kind of shipping limit in terms of their area. We had clean node detailing. We did a lot of structural analysis to make sure that this really worked right and our sizes were as minimal as possible. The general contractor just handed the subcontractor a CAD and they produced something that I find extremely offensive. They did not look at their drawings. They just applied one size everywhere. Maybe this is like kind of narcissism of small differences or something, but I think that's a very upsetting picture compared to what we started with. And there were some pretty tense meetings where we said, guys, you're not coming in here, out of nowhere. Can you get closer to what we did? Can you take into account some of these nuances to give us something that really shines? Maybe this is like corporate is trying to ask you the difference between these two pictures. They're the same picture, but to me, I find the one that they came up with very upsetting. And I think we ended up getting something that was much nicer. So, but it took, honestly, like when you're working with a contractor, they'll say, oh, this is going to kill the cost. And what they mean is it's going to kill our fee. And you kind of need to just throw elbows a little bit. I mean, I'll be honest, guys, I was highlighted as a risk to the general contractor to the owner for not accepting the design, quote unquote. So I'm glad we finally got on the same page and got something that I think is a little bit nicer. On the coordination side, like you got to be there through all the coordination meetings. There's nothing worse than having a drain pipe that's bigger than your structure, right? So if you have, for this particular type of grid shell structure, you don't want a big gap between the glazing and the steel. It'll make things look twice as deep. We did need a gap for detailing, right? With this particular subcontractor, that's how they wanted to do it. And we tried to use that gap to stuff this sprinkler pipe and conduit into it. Like everybody's got to go through the boring part of coordinating things, or you'll end up with sprinklers on the bottom of your structure. I mean, we even made sure to paint them the same color as the rest of the structure, right? This is like not what they teach you to do for engineering in school, but if you want something that looks good, you have to go through that level of detail. I don't have any, finished pictures of this because it's not built yet, so let's hope it looks that good. We'll see how it gets executed. But I mean, I don't have any like, I don't know, sort of profound ways to sum this up other than you have to kind of be able to, gently throw elbows, right? And stick around through the coordination process because, contractors are going to react to this and see a lot of complexity and try and dumb it down. And to a certain extent, you got to bend and work with them. To another extent, you got to protect the design. And I feel like I was kind of the architect's favorite engineer because of, putting myself in that position. Little plug, and then I'll cut. I think I'm almost at time. As The only thing I'm going to advertise is that I'm working on academic research to make some of these form finding techniques more accessible to architects, right? You know, over the course of my career, I realized that it doesn't work to say, hey, you guys are doing it wrong, do it the mathematically correct way. I've had to kind of back up and say, you know, what is the way that architects like to work, right? You typically, in my experience, you want to do a NURB surface and you kind of project some grid onto that shell, right? So with an academic collaborator, Japanese academic collaborator, Masaki Miki, who did 95% of the work on this, working with academics is fantastic because of that. We have, you know, sort of algorithm where you can draw the shape you want, try and project the grid you want onto that, and it will force that grid towards equilibrium, okay? And flat panels. So this is an interactive thing. It runs on a GPU, okay? So you can actually work with it at interactive speed. And it can be hopefully something that trains your insight on an intuitive level of what shapes work well without us having to come to you and say that doesn't work, okay? Got some decent looking results, decent looking control over the shape. It's free. I do think that's important. Like, this is not stuff that should be proprietary. That's part of the whole benefit of working with academics, that Bill Baker paper from 1992 was openly published and everybody copied it. I hope everybody copies this. But if it doesn't work for you, let me know. That's all I really have, so I'll stop there.